Okay, so we've really dug into this idea of a process, right? This neat abstraction, giving every program its own virtual CPU, its own private memory, feels very self-contained.
It does, it really does. But now we're peeling back another layer, moving inside that process to talk about threads.
Right, threads. So what are they exactly? Still part of the same process?
Exactly. Think of it like a single process that suddenly has multiple places it can be running code at the same time. Multiple points of execution.
Multiple program counters, essentially.
You got it. Each thread has its own private registers, its own stack, that's its thread local storage, and its own program counter. But, and this is the absolute key, they all share the exact same address space, same memory.
Ah, okay. Shared memory. And that's our mission for this deep dive, isn't it?
Yeah.
Figure out why that sharing is, well, good, but also why it leads to some major headaches.
Precisely. The benefits versus the complications. It's the core challenge of concurrency.
All right, let's start with the good stuff. Why bother with threads? The sources mention two big reasons. First one seems straightforward. Speed. Parallelism.
Yeah, pure performance. If you've got work that can be broken up, like processing parts of a big array, and you have multiple CPUs or cores...
You just throw a thread on each core and boom, faster calculations.
Exactly. Get that parallel speed up.
Makes sense. What's the second reason? Sounds a bit more subtle.
It is, but maybe even more critical in day-to-day systems. It's about avoiding blocking, keeping the CPU busy. Utilization.
Blocking.
Yeah.
Like waiting for impute. to happen.
Exactly that. Imagine one thread needs to read from a slow disk or fetch something from the network or even handles a page fault. It gets stuck, right? Blocked.
Yeah, it just waits.
But if you have other threads in the same process that are ready to run, the OS scheduler can just instantly switch the CPU over to one of them.
I see. So while one thread is twiddling its thumbs waiting for the network card, another thread can be doing actual work.
You got it. It lets you overlap computation with that slow I/O. Super important for things like web servers, database systems, anything that waits a lot.
And switching between these threads,
Yeah.
that's much faster than switching between whole processes, right?
Oh, way faster. Because the address space, the page table stays the same, you don't have that huge overhead, no TLB flush. It makes concurrency really, really cheap.
Almost free.
Well, almost. But here's the catch we hinted at. Because the OS scheduler is just switching whenever it feels like it,
Oh.
the order things run in becomes unpredictable. Totally indeterminate. Maybe thread A runs for a bit, then B, then A again. Or maybe A runs entirely, then B. You just don't know.
Okay, indeterminacy. That sounds like where the problems start. Let's use that classic example.
Yeah.
The shared counter.
Right. Simple setup. You have two threads. Each one loops, say, 10 million times, and inside the loop it just does counter, counter plus 1. Counter is a shared global variable.
So basic math tells us, start at 0, two threads each add 10 million. Final answer should be 20 million? Easy.
Should be.
Okay.
You run this code, and maybe you get, I don't know, 19,345,221. That's not right. Nope.
Yeah.
And run it again. You might get 19,221,041, or some other wrong number. It's different every time.
Why? How can adding one go wrong? It seems so simple.
It looks simple in C code. Counter equal counter plus 1. But that one line isn't one atomic step for the computer.
Ah, right. Machine instruction.
Exactly. That line breaks down into maybe 3 low-level instructions, like on MB86. First, load the current value of counter from memory into a CPU register.
Okay, got the value.
Second, add 1 to that register.
Increment it.
Third, store the new value from the register back into memory where counter lives.
Load, add, store. Okay, so what goes wrong?
The scheduler, it can interrupt the thread between those instructions. Imagine counter is 50, thread 1 loads 50, it adds 1, so its register now holds 51.
Ready to store 51.
But before it stores, boom, context switch.
Mm-hmm.
The OS pauses thread 1 and runs thread 2.
Okay, thread 2 is...
Thread 2 comes in. What value does it load for counter from memory?
Well, thread 1 never stored as 51, so
Yeah.
it must still be 50 in memory.
Bingo, thread 2 loads 50. It adds 1, gets 51 in its register, then it stores 51 back to memory, so counter is now 51.
Okay.
Now, eventually, thread 1 gets to run again. What was it about to do?
It was.
Ah,
It was about to store its value, which was also 51.
right. So thread 1 resumes and stores 51. We had 2 increments execute. Both threads loaded 50 and computed 51. But the final result in memory is just 51. We lost an update.
Wow.
Oh.
Okay, that totally explains the wrong final count.
Yeah.
And because the timing of that interruption is random.
The number of lost updates is random, leading to those unpredictable final results. That's the race condition, or it's sometimes called a data race. The result depends on the exact timing lottery of the scheduler.
And the program becomes indeterminate. The output isn't fixed.
Correct. And that little sequence of instructions, the load, add, store that accesses the shared resource counter, that's what we call the critical section.
The dangerous part.
Yeah.
The part that can't be interrupted incorrectly.
Exactly. It's the code that needs protection. What we need is a way to ensure mutual exclusion. Meaning only one thread can be inside that critical section at any given time. If thread 1 is doing its load add store, thread 2 has to wait until it's completely finished.
Like making that whole sequence behave as one single, uninterruptible step.
That's the goal. We want atomicity. All or nothing. Sequence completes fully or it doesn't even start. And achieving that requires special tools. Synchronization primitives.
Built using help from the hardware and the OS itself, I assume.
Absolutely. Things like locks, semaphores. We'll get into those, but yeah, they're essential for managing these critical sections.
And it's not just for protecting shared data updates, right? You mentioned waiting, too.
Yeah, synchronization is also crucial for coordination. Like thread A produces some data and thread B needs to wait until that data is ready before consuming it. Or waiting for I/O to finish, like we discussed earlier.
So it's a fundamental problem.
Totally fundamental. How do you build these synchronization tools correctly and efficiently? It's a huge part of systems design. And interestingly, the problem really first showed up in a big way inside operating systems themselves. The OS kernel was the first major concurrent program everyone had to get right.
Which leads to a really interesting final thought. If the OS itself is managing all these processes and threads, its own internal data structures, like the list of processes or file system information or page tables, must also be shared resources, right?
Oh, absolutely. Kernel code running on behalf of different processes or handling interrupts, it's all accessing shared kernel data.
So how does the operating system protect itself from these exact same race conditions we just spent all this time describing? How does the OS manage its own critical sections?
That's the million-dollar question, isn't it? Something for you to ponder.